Hi, my name is Fernando Mendez, and this is my presentation on secure IT design, EDA algorithms, and methodologies. So the typical EDA workflow is shown to the left. EDA here stands for Electronic Design Automation, and it is a powerful tool for easy design optimization. Uh, as you can imagine, creating an IC design that is power efficient and fast is very difficult to do by hand. Uh, so EDA tools exist to help the IC designers do this. And while these tools are powerful in doing so, um, they weren't exactly implemented with security in mind. For example, as you will shortly see, one of the one of the um, one of the most powerful vectors of attack are SEAs, which are side channel attacks, and these could result from optimizations done by EDA design tools. Another avenue of attack, which could be introduced by EDA, are Trojans, which are introduced through the supply chain management, particularly through the use of third-party libraries. Um, so that being said, we'll go on to discussing our security issues. There are three separate topics we will address today, which are side channel attacks, piracy, counterfeiting of ICs, and hardware Trojans. So side channel attacks are attacks that are carried out on physical channels from which information can leak. There are two major sources of information leakage. The first being circuitry. Um, Basically, the type of attacks that are carried out on uh, this leakage source are CPAs, which are correlation power analysis. Um, CPAs they basically rely on a power signature that of a particular set of gates from the circuit, and these can reveal sensitive information with regard to like the advanced encryption standard or private circuits, secret keys. And of course, you never want to reveal information regarding that. Another source of information leakage, which we won't be discussing, is it comes from the architecture, and some information that could be garnered from architecture comes from an example, time behavior of caches and modern processors, um, which could result to attack avenues like speculative execution. What you see on the left is a TVLA test, which is test vector leakage assessment. And this test is done on power consumption. Um, in this example, the power consumption of prior circuits. And this tells the designer how susceptible they might be to SEAs based on how much information can leak from the power consumption. So private circuits are circuits that were intended to provide some sort of secrecy against SEAs. Unfortunately, they leakage can still occur from this type of circuit because of the optimizations carried out by netlists. So here, this is where lazy engineering can be problematic. Lazy engineering refers to just allowing EDAs to freely optimize your circuit. So even if you implement this private circuit correctly in like a high level language or whatever, uh, your EDA optimizations may result in SEAs. So one of the ways this could happen is that the EDA doesn't appropriately account for delays, uh, particularly delays of random bit arrivals. As you see in the top figure, the random bit R12 takes a little bit of time to arrive to the XOR. This is problematic because if it doesn't arrive, this could reveal some sensitive information regarding the key, and attackers can reveal this information using SEAs. Another problematic avenue is out of order execution. Um, with out of order execution, the EDA will optimize an algorithm to execute out of order. Uh, and as the algorithm, this could be correct because it still reveals in the same output, but the behavior is still not acceptable because this will still give off a signature power consumption, which could be used in SEA attacks. So to mitigate this, secure private circuits can be implemented as what's done in this paper. So as you saw on the left, the TLVA test showed readings that fell out of the acceptable range of ±5. And this resulted in the secret key to be guessed correctly, as you can see by the average key ranking, where the correct average key ranking is 2. On the right, you see the TVL lay test, where of the appropriately implemented private circuit, it was able to stay within the acceptable ranges, and the secret key was unable to be guessed. This secure private circuit was implemented by appropriately accounting for the out of order execution of the algorithm that would have resulted from freely optimizing the circuit using EDA. Also, the synchronization of the vulnerable logic gates, for example, like when the random bit would arrive, was appropriately accounted for. Of course, there's a performance trade-off to be made here with by accounting for these mitigation techniques results in there being more overhead and as a result, worse performance. So next we'll be discussing piracy and counterfeiting of IC design. So piracy and counterfeiting of IC design is problematic because one, it leads to unauthorized production of chips. So this is essentially stealing. 2, out of specification, defective ICs can make their way to market. And as you can imagine, this is harmful, particularly in critical environments. In my mind, I'm thinking of like factories where chips need to be absolutely like they just can't fail. So these out of spec chips can make their way in there, so that could result in there being all sorts of problems. So as you can imagine, there has been techniques that have been implemented to mitigate this. For example, the encryption of functioning circuits. So here's like a basic logic gate, Boolean function implementable logic gates. And on the right, you see that being encrypted slightly using 1 key bit. Without this key bit being set, which here the correct value is 1, and this is an XOR gate. Without it being set, the device won't function appropriately. So this is one way that designers have got around that piracy or counterfeiting. But as you can imagine, algorithms like these have been developed to basically side skirt this. So this led to designs like this to be developed. So these designs use scan chains to make it more difficult to figure out like what are the key bits. So, and this still isn't completely foolproof. There has been techniques shown where these bits informations were able to be extracted using like faster clock cycles during extraction periods. So as we'll get to, there has been a proposed solution to that, but basically any mitigation technique has to satisfy the following. There has to be reverse engineering resistance, so satisfactory key length, like for example, satisfactory key length needs to be long enough to basically overrule any brute force attempts. The key has to be obfuscated, and this is usually done by spreading out the key bits like pretty uniformly to hide its significance. Keyless testing needs to be implemented, which is done in this proposed solution. That is because key testing needs to be done on this IC to make sure it works properly. So without key, like without without giving up the key, that testing needs to be implemented some way. Um, and these two relate to the basic things, the basic way that things are done currently. These are pretty complex as it is, so and any added complexity will probably not make it worth to implement this proposed solution. And what's proposed here is kind of what you saw here. It's just like an added mux gate was implemented here, and this is to prevent any multi-cycle readings of the scan chain to try to reveal any information regarding the secret keys. There are 3 modes here. So the mode that's used by the scan chain is mode 2, where the tool generation tool, where the test generation tools are used to load these logic codes are basically components, like combinational components. So think this is like a logic code. So these are just filled with like test inputs, and that is done in mode 2. And mode 1 is when these are operating functionally and the outputs are able to be tested. And mode 0 is used in the secure site, usually the design house, and that's where the secret keys are programmed. So yeah, this prevents any readings, any multi-cycle readings that will usually reveal its sensitive information regarding the secret key. This is typo, it should be 3 modes. But to really prevent any readings to the secret key, there needs to be some sort of restriction on mode switching. So like, post activation. And this is done using this implementation. So this compressor is used by design houses to implement testing. And this is where like key information can be revealed. So you can see by this implementation, when the foundry tries to flip this test to, I want to try to flip this mode to testing, it'll result in only once being outputted. And this is usually undone by a hard reset. But yeah, when they try to get at an activated circuits testing stuff, testing circuits, they can't, because all they'll get out of here is just meaningless bits, essentially just all at once. So they won't be able to extract any information. I forgot to mention, but in order to extract any information from this, they need to use an activated circuit to test against. So they'll like put like a bunch of test inputs to like the testing to the testing cells, basically scan chains, and they'll watch it for the correct outputs, and they use those outputs to test against. They're basically their guesses were for the key bits. So this is the proposed design flow with 3 stages here, being the lock insertion, the DFS, the time for security, and the activation stage. So lastly, we'll be discussing hardware Trojans. So hardware Trojans, their purpose is wide-ranging, as you can imagine, 2 being to leak information and to disrupt IC performance, which can both be disastrous. This usually occurs in outsourced supply chain management. Modifications can happen at system level, RTL level, or gate level, and these type of Trojans can always be on or triggered internally or externally. One of the proposed solutions against this is Camouflage Smart Fill. This is pretty easy to explain. Basically, you have your initial design. This is fully functional. How you intend your design to operate, and you take it and you just fill it in with more layers to obfuscate your design's purpose and signal lines and whatever. It makes it more difficult to reverse engineer. What this also does is it reduces the amount of space in which a Trojan can be inserted. So it makes it that much more difficult to implement a Trojan attack. Another method is camouflage logic cells. It's very similar. Instead of filling in space, cells are camouflaged to obfuscate their true function. So as you see here is a NOR gate, and on this picture on the right is a camouflage NOR gate. So it's pretty difficult to figure out that this is a NOR gate based on this NOR gate. So yeah, this makes it more difficult to reverse engineer. So more difficult to carry out a Trojan attack, as well as more difficult to pirate in IC design. And here's the proposed design flow. Basically, the way I look at it, this is kind of done hand in hand. Like as you go along your normal development, you'll carry in some models and backend models when you're doing your backend design. So it basically becomes a part of your design flow that you have to like introduce and accommodate. So again, with this, similar to the past two designs, there has to be some trade-off made to performance. So you can imagine implementing something like this will result in there being more power consumption, and as a result, there being more delay through stuff like added capacitance. And yeah, that's just a trade-off you have to make between wanting to make your design hard to implement a Trojan attack. But again, these trade-offs can be made with more context on your design. So just some final remarks. EDA design tools are great in optimizing your IDC design. They help shorten development time, but great care must be taken in using them, especially if you're working with secure applications. So there can't be any shortcuts taken. Just as we saw in the example with secure private circuits, even though the design is inherently secure, IDA tools can lessen that security and make it vulnerable to other vectors of attack like SEAs. So great care has to be taken there. And even with that, some sacrifice needs to be made, maybe in the form of performance. That just might be a necessary evil in some cases, given the context of how security design needs to be done or made. Further, preventing piracy is complicated, but there's always new techniques being made. Again, some trade-offs need to be made there. Depending on how valuable your design is, you may want to make those trade-offs. And the same thing could be said for preventing Trojans. Similar argument goes there with the security. Given the context of it, you may need to take on that performance trade-off for security. That's my video. Thank you for watching.